Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. This section is a brand new section of the course. These are all supplementary lectures about backpropagation. That means if you already understand backpropagation, then you can safely skip this section and move on. So what's covered in this section? This is really just a collection of updates I've made to the course over time, to help students out who are having particular difficulties. So there are some mechanical lectures to help you get through the hard parts of backprop. There's also some meta discussion about why you need to know backprop and how it can be useful when you're tuning a neural network in the future. There's also a background lecture on gradient descent if you don't remember how that works. So if you need some extra help understanding backprop, this section is for you. Otherwise, feel free to skip it. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. A lot of people ask me, why do we need to learn backpropagation? Don't libraries like Theano and TensorFlow already do that for us? And of course, these libraries make writing complex neural networks very easy, easier than they have ever been in the past. Libraries like TensorFlow allow you to only have to define the forward pass and the cost function. Since backpropagation can be derived mechanically, the entire learning process can be determined automatically after we've defined how to build the neural network and how to build the cost. In fact, deriving the equations for backpropagation is so tough that most courses just won't do it. What they usually do is skip over it and claim, like, oh, it's not intuitive or some other nonsense. Actually, I think backpropagation is very intuitive. It's no different from thinking of a ball rolling down a hill during gradient descent. If you can minimize x squared or x squared plus y squared in 2 dimensions, and you can understand that, then you can understand backpropagation. It's really the same thing. So typically, the 2 approaches I see go something like this. Number 1, you immediately go from 0 to hero by learning how to build a neural network using a high-level library like Keras, or maybe if you're lucky, Theano or TensorFlow. For me, that is totally unsatisfactory. I want to know how these functions work, not just how to call them. You are in a deep learning course. So if all I'm given are some facts about how some API works, then I'm not really doing deep learning. I'm just learning how to read documentation. And that's something any sufficiently knowledgeable programmer can do by themselves. You don't need a course for that. In these situations, who's the one really doing the deep learning? Well, it's certainly not you. It's the guy who wrote these libraries. So if all you're doing is plugging your data into Keras, then I'm afraid that the course you've taken is a little unethical. They promised to teach you deep learning, and instead they replicated some existing documentation. The number 2 approach I see is that you are provided with the update equations for backpropagation, and then you're given the pseudocode, which is basically to run through the same loop again and again. While this is a little better, it's still unsatisfactory. The most astute among you will dig deeper and ask, well, where did these equations come from? Why are these the update equations? Why not some other equations? Why are they this way and not some other way? Personally, I think this makes things harder to understand, because let's face it, these equations are complicated. What makes them easier to understand is knowing where they came from and understanding why each part is there. So I think it's very important to understand why you're writing the code you're writing. It wasn't just invented from thin air and just miraculously started working. It's just some basic calculus and probability. So why is backpropagation so important to the study of deep learning? Well, it's the basis behind every neural network you're going to learn about in the future, from convolutional neural networks to LSTMs. There are some other articles out there written by professional writers who do a better job than I ever could at describing the importance of backpropagation. So let's look at one such article. The peculiar thing about deep learning is just how old its key ideas are. Hinton's breakthrough paper was published in 1986. The paper elaborated on a technique called backpropagation, or backprop for short. Backprop, in the words of John Cohen, a computational psychologist at Princeton, is what all of deep learning is based on. Literally everything. When you boil it down, AI today is deep learning, and deep learning is backprop, which is amazing considering that backprop is more than 30 years old. It's worth understanding how that happened, how a technique could lie in wait for so long and then cause such an explosion, because once you understand the story of backprop, you'll start to understand the current moment in AI. So these are the people at the epicenter of deep learning telling you how important it is. It's what everything we do in deep learning is based on. So if anyone ever tells you you don't need to know backpropagation, just call this function, ask them, are you teaching me deep learning, or are you teaching me this API's documentation? Now, other than this very big reason to learn backpropagation, you might wonder, are there other reasons? Maybe all you want to do is build deep learning systems and you don't really care about how they work internally. And the answer is yes. There are some very practical reasons where it's better for you to understand backpropagation than to not. So let's go over some examples. Firstly, there's the vanishing gradient problem. Without understanding what the backpropagation equations look like, you can't understand this. Let's look at the derivative of the sigmoid. We can see immediately that once the input gets large enough in magnitude, the gradient goes down to 0 very quickly. And since we are doing gradient descent, if your gradient is 0, then your update is 0, and your parameters will not get updated. But that's not the only problem. Researchers have found that deep neural networks work very well at learning and generalizing. But if you notice, the maximum of the sigmoid derivative is 0.25. So at best, every time you go back a layer in your neural network, you multiply by another 0.25 in your weight update. And this is just due to the chain rule. The further back you go, the more multiplications you have to do. What happens when you multiply something by 0.25 repeatedly? It goes down to 0 at an exponential rate. Another problem which is related to this has to do with the ReLU. Notice that with the sigmoid and tanh, the slope never actually reaches 0 unless it's due to numerical imprecision. With the ReLU, the slope is exactly 0 if the input is less than 0. So if all your inputs and weights happen to be configured in a way that leads to the ReLU always outputting 0, then you're effectively doing lots of wasteful computation. Researchers have shown that up to 40% of a neural network can be made up of these dead neurons. And of course, in order to understand this, you have to understand derivatives. And if you understand derivatives, then you can understand backpropagation. On the opposite end of the spectrum, we can also have exploding gradients. This happens in the realm of recurrent neural networks. What happens in a recurrent neural network is that you end up multiplying by the same weight matrix again and again. Intuitively, if you think of a scalar and you multiply it by itself over and over, one of two things can happen. We already saw what would happen if the scalar is small, in particular less than 1. This product is going to go down to 0. But what happens if the scalar is bigger than 1? Then we get exponential growth, and this product is going to explode to infinity. So, and this requires a little knowledge of linear algebra, if the eigenvalue of your weight matrix is bigger than 1, then you're going to get exploding gradients. Now there are a lot more stories and examples we could go through as purely practical examples of why backpropagation is important, but I think what we've discussed so far is sufficient. If I had to summarize it quickly, I'd say backpropagation is going to make you much more effective at debugging neural networks and neural network training. A lot of people are looking for plug-and-play solutions, but if you're not familiar with the details, then it's hard to answer questions like, how can I improve this? Or how can I figure out why this isn't working? So overall, just understanding backpropagation will make you better at deep learning, whether that's making new and better things or fixing things when they're broken. Hey guys, and welcome back to this class. Unsupervised Machine Learning, Hidden Markov Models in Python. In this lecture, we are going to take a close look at gradient descent, since it's used extensively in deep learning and is general enough to be useful in a wide variety of situations. The idea is this. You have a function you want to minimize, and you want to find the optimal inputs to minimize this function. Usually this thing we want to minimize is the cost or error function. We can maximize things too, like when we want to maximize the likelihood of some probability distribution, and to do that all you need to do is reverse the signs. To demonstrate this, we are going to do a very simple one-dimensional example, although usually in machine learning we are working in more than one dimension. This will help us visualize what's going on. So let's take a simple function, j equals w squared. We know that the minimum is at w equals 0. Our weights are randomly initialized, so suppose we begin at w equals 20. We know the gradient dj by dw is 2w. Let's make our learning rate 0.1. So on our first iteration, we get w minus learning rate times the derivative, so that's 20 minus 0.1 times 40. That's 16. So we set w equal to 16. On the next iteration, we get 16 minus 0.1 times 2 times 16. That gives us w equals 12.8. On the third iteration, we get 12.8 minus 0.1 times 2 times 12.8. That gives us 10.24. So you can see that on each iteration, we get closer and closer to 0, but we take smaller and smaller steps because when we get closer to 0, the slope gets smaller. Let's try this in code and see if we can get all the way to 0. Alright, so I'm going to start by importing NumPy. Okay, we're going to set w equal to 20 for I in x range 30. W equals w minus 0.1 times 2 times w. Okay, and we're going to print w on each iteration so we know how it improves. Okay, so w gets down around 0.2. So it looks like 30 steps isn't close enough. So let's try 100 steps. So we're going to reset w to 20. Move through 100 steps. W equals w minus 0.1 times 2 times w. Print w. Alright, so that brings us very close to 0. So there you have it. I hope you are now convinced that by moving slowly in the direction of the gradient of a function, we get closer and closer to the minimum of that function. Now, why is this technique so important and why do I keep talking about it? Well, you'll notice that as we progress through deep learning and machine learning, the functions that we'll work with will get more and more complicated. For regular neural networks with softmax, it might take you a few hours or a few days to get the derivatives right on your own the first time. What happens when we go to convolutional neural networks and recurrent neural networks? It's definitely possible to derive the gradients on paper, but we don't actually want to spend our time on this. Our time is much better spent testing different architectures and different hyperparameters without having to worry about the gradients. We can use libraries like Theano and TensorFlow to calculate the gradients for us. However, it's good to understand what's going on, because then gradient calculators become another tool in our machine learning toolbox, and we can use it on anything, even things like hidden Markov models. As an exercise, try manually calculating the gradient and finding the solution for this cost function using gradient descent. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, I'm going to provide a helpful hint for deriving the backpropagation algorithm. The hardest part is the softmax portion, both the softmax derivative itself and then putting it back into the full derivative for the chain rule. My goal in this course is to encourage you to think through it yourself, so you should only watch this after you spent at least a few days trying to do it on your own. Note that doing this doesn't actually require any new skills other than differential calculus. The only problem you will most likely come across is that you have to be very, very careful because it's easy to make mistakes. But again, no new skills are needed beyond taking derivatives. Let's start with the definition of softmax. The tricky part with this derivative is that we'll need to take the derivative with respect to ak, or any other ak prime where k prime is not equal to k. These will give you two different results, because if you take the derivative with respect to ak, both the top and bottom portion are functions of the variable you're taking the derivative with respect to. If you take the derivative with respect to ak prime, where k prime is not equal to k, then your differentiating variable only appears on the bottom. So let's take the derivative with respect to ak first. The first step is to expand the derivative using the product rule. After calculating the individual derivatives, we get this. And we can see that this is equal to yk minus yk squared. Next, let's take the derivative with respect to an ak prime where k prime is not equal to k. We see that we only need to take the derivative with respect to the bottom term because the top term is constant with respect to ak prime. We can give one of the sums to ak and one of the sums to ak prime so that we can again phrase the answer in terms of y. So it's equal to negative yk prime. Using these two results, we can combine the derivative to get it all in one equation using the delta function. The delta function is 1 if its two arguments are equal and 0 otherwise. Note that both these forms are equivalent, but only one of them will be useful in the backpropagation derivation. When you're doing backpropagation, you're going to be summing over k prime as your summation index, but you'll be taking the derivative with respect to k. So it's going to look like this sum. So we of course want the k prime to be on the outside so that the top y and the bottom y cancel out. One place I always get stuck is how we turn this into just tnk minus ynk, where the k prime and the summation disappear. The first thing we want to do is look at the summation for both terms individually. We can see immediately that the first summation goes away because delta is only 1 when k is equal to k prime. It's usually the second summation that stumps people. The trick is to seeing that the y doesn't depend on k prime at all, so it can be brought outside the sum. And then finally, since only one of the targets can be 1, while all the others have to be 0, then the sum over all the classes must be 1. Therefore, we end up with the desired equation, tnk minus ynk. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to talk about common issues students have with backpropagation. This lecture is in the appendix because I really want you to spend a considerable amount of time trying to do this yourself before you watch this lecture. It's not intended to be a main part of the course, just something you look at if you really need help. In this lecture, I'm going to show you that this derivation really only requires rules of calculus that you already know from first-year calculus, and that the real trick is simply being careful. This is the best kind of homework problem, and you should treat it as such. It's a homework problem where the answer is already given. So there's no guessing. You know what rules you have to apply, and you know what the end goal is. If you fail to reach that goal, you know that this is a failure in your ability to consistently apply the rules of calculus. And so basically, it's just a test of your calculus ability. Can you debug your calculus to figure out which steps were wrong, or where you made an assumption that wasn't true? Before we get into the details, let's just remind ourselves of the lettering conventions. T is the target. Y is the output prediction, which is a probability. A represents the activation, the value right before we put it through the activation function. We usually use A for the activation at any layer, but for this lecture we will specifically be referring to the final layer. Z is the hidden layer value, and X is the input vector. The size of X is big D and will be indexed by little d. The size of Z is big M and will be indexed by little m. The size of Y is big K and will be indexed by little k. The input to hidden weight is W and its size is D by M. The hidden to output weight is V and its size is M by K. So first we start with the cross-entropy loss, which I'm sure you're familiar with by now. We know we want to find the derivative with respect to the neural network weights. We'll say VMK for the hidden to output weight and WDM for the input to hidden weight. We'll derive the expression for V first, since it's shorter and easier. The first place that people usually get confused is that we have to change the summation index. We put a prime on the summation variable, but it could just as well be another letter. Why do we want to do this? Well, consider a simple linear equation, y equals w1 times x1 plus w2 times x2 plus w3 times x3. If we consider the w's to be parameters, then we can define three partial derivatives, dy by dw1, which is x1, dy by dw2, which is x2, and dy by dw3, which is x3. Now, of course, we can write y compactly as the sum over I equals 1 to 3, wi times xi. You might think, well, this is easy. You can just define dy by dwi to be xi. But this is only because this equation is very simple. It's actually a mistake. The mistake you make in assuming you can do that is forgetting that on the right side of the equation, I is only an index. It changes from 1 to 2 to 3. On the left side, I is meant to be constant, referring only to 1, 2, or 3. Therefore, it's more correct to sum over I prime on the right side, meaning I prime is a changing variable, whereas you take the derivative with respect to wi on the left side, meaning I is a constant. Equivalently, you can just use a different letter entirely. It doesn't make any sense to take the derivative with respect to a changing variable, because you can only have one specific partial derivative at any one time, either dy by dw1, or dy by dw2, or dy by dw3. But the key is you have to pick one. It's not the same as the summation index. So by giving the summation index the same letter, it's sort of like bad programming practice where you use the same variable name for two different objects. Let's phrase this another way. The right-hand side summation index is only a dummy variable or a temporary variable. In other words, it doesn't matter what we name it. We can literally name it dummy. Because of this, it's poor style to give it the same name as the index on the left-hand side, because the fact that they are the same would be purely a coincidence, and therefore can lead to mistakes due to the fact that you mistakenly think they are the same. To further reinforce why this is a bad idea, let's do a programming analogy. Suppose we have a function that takes as input the variable I. I represents some important input which we want to make use of. Now I enter a for loop where the dummy index variable is I. So I say for I in x range n, do some task. Now my original argument I has been completely erased by the index variable. This is clearly not a good idea. The next problem people have is splitting this up via the chain rule properly. Here's what we know. We know how to take the derivative of j with respect to y. That's essentially just the derivative of a log. We know how to take the derivative of softmax. That can be complicated, but I've already shown you all the steps multiple times. Remember that the trick is that the output of the softmax depends on the value at each node, because it has to divide by the sum of the exponential over all the nodes. Therefore, while we are summing over k prime, we are actually taking the derivative with respect to vmk. Vmk only affects the activation ak, but the activation AK can affect any of the YK primes. We also know how to solve the final derivative on the right, which is just the derivative of a dot product. We know how to do that from linear regression, and we also saw an example just a second ago. The most complicated part for people is the second term, the derivative of softmax. In particular, why it's k prime on top but just k on the bottom. We can see this more clearly if we go back to our simple dot product example. We know that the partial derivative is going to have I prime in the top, since that is the function we want to differentiate, but it's going to have I on the bottom, since that's the variable we want to differentiate with respect to. So here is a clear example of where we have I prime on the top and I on the bottom. Remember, the I prime is just a dummy variable summation index, whereas the Wi you're differentiating with respect to is a specific variable. So now going back to our chain rule, we have these three individual partial derivatives. We split up the problem into easier parts, and we already know how to solve each part. The first part is just the derivative of log. You know that from first year calculus. The second part is the derivative of softmax. You know how to do that because you can combine the product rule and the rule for exponentials. The third part is the derivative of the dot product, and you already know how to do that because we just did an example a second ago. And then the last step is just to multiply these three things together and simplify. You already know how to simplify the softmax portion since we already have a lecture on that. So what about W for the input to hidden layer? For this, we should make use of some helpful facts in order to avoid duplicating work. In particular, we already know how to take the derivative of the softmax up to the activation A. In other words, we can say dj by dak is equal to tk minus yk. You'll see why this particular derivative is useful very soon. The next thing we have to make use of is the partial derivative chain rule. This involves the sum and product. In particular, if x is a function of t and y is a function of t, and f is a function of x and y, then we can write the total derivative, which is df by dt, as the sum of the products of each individual component derivative. And of course, we can extend this idea to any number of variables, and we're calling that k here for obvious reasons. So f is a function of all xk, and all xk are a function of t. So we can apply this same idea to the cost function j. Notice that you have to be careful which variables you break up with the chain rule. We know that we're going to have to sum over k, for the simple fact that k does not appear on the left side of the equation, and therefore, according to the chain rule for total derivatives, we need to sum over all the possibilities. So before we had the situation where f is a function of all xk, and all xk are a function of t. Just by simple renaming, we can say that j is a function of all ak, and all ak are a function of wdm. The trick is to break it up at the activation A. Since, as we discussed earlier, we know the derivative of j with respect to a, that's just t minus y. And we know the derivative of a with respect to z, that's just vmk. This is just the derivative of the dot product, which we've done twice already in this lecture. Note that here we're still using A to mean the activation right before we apply the softmax in the final layer. The rightmost derivative shouldn't be too hard at this point. I've assumed we're using the sigmoid activation function, but we know the derivatives for all the other activation functions too. Here I'm just substituting u for the activation at the hidden layer. And since u is just a dot product, we already know its derivative, it's xd. Finally, we can combine all these terms together, and we arrive at the expected answer. For these examples, you'll notice that we assumed there was only one sample, so we didn't sum over n. Why is this not a problem? Well, this is another one of the basic rules of calculus. The derivative of a sum is the sum of the derivatives. Since the cross entropy is just the sum of the individual cross entropies for each sample. We just need to sum the derivatives we just found over n. And all the relevant variables, y, z, and x, would be indexed by their sample index n. As an example, let's take the derivative with respect to vmk. If we have n samples, that means z will be indexed by n, and all we have to do is sum all the individual derivatives over n, and we get the expected answer.